Hey, we're going to look at solving systems of three equations, but we're going to do it using something called an augmented matrix. This is pretty fun, and it's a nice precursor to a course called linear algebra. You're working with matrices a lot, and we're going to do a couple examples here. Now, the technique we're going to look at is called Gaussian elimination. I'll write that down shortly. And there are other ways to do this as well, but we're going to focus on Gaussian elimination. So here's our first example, and the reason we're going to use this technique is because this works for higher dimensional systems as well. This is a 3-equation system with 3 variables, but it can also work with a 4-variable system and 4 equations, or 5 and 5 and 6 and 6, etc. And so you can easily extrapolate this to higher dimensions. We're only going to do 3 equations in this video, but you should get the idea. Now, we're solving using Gaussian elimination. So the first thing we're going to do is convert this system to what we call its augmented matrix. And that's pretty easy because this system is already set up where each equation is in standard form. We have an x term, a y term, a z term equals a constant. You can see all 3 equations are written that way. And so when we convert this to its augmented matrix, it turns into just basically a table of coefficients. So row 1 here turns into the coefficients 2, -1, +1, 11. Row 2 turns into 3, 2, -1, -5, and last we get 4, -2, -5, 1. So we have this table of values. Now, to put it into matrix form, we put these brackets around it. Sometimes parentheses are used. And to make it an augmented matrix, because it's not just a table of values, each row represents an equation, and we indicate that by putting a vertical line where all of the equal signs are in the equations. So now we understand that this is the x column, the y column, the z column, the equals column, and the constant column. So this is our augmented matrix. Augmented matrix. Now, what's our goal here? So our goal is what we call row echelon form. We're going to modify this table of equations into a new table of equations where it looks something like this. We'll have our first column will be some number, and then below it we'll have zeros. Then our second column will be some number, and below that will be a 0. And then our third column will be all numbers, and our fourth column will be all numbers. The key to this is that we get this sort of triangle of zeros, okay? This is often called an upper triangular matrix because you get this triangle of numbers above with a triangle of zeros in the bottom left corner. So that's our goal. And we're going to do it in the order that I mentioned. We're going to work column by column. We're going to work in column 1 first, then we'll work in column 2 second. And our goal is to create 3 zeros. Okay, so let's work in column 1 first. So how do we create the zeros in column 1? Well, we use the entry that's not a 0 in column 1, the 2 up here. And so I need to use this 2 to eliminate this 3. And so I can do that because remember, the rows represent equations. If I can turn these both into the same number with opposite signs, when I add them together, they will cancel. So the way I'll do that is I'll take and make, let's make row 1 into +6 here, because 2 and 3, I can easily turn both of those into 6. So I'm going to take 3 times row 1. Remember, that's going to give me a +6 here. So that means the 3 in row 2 needs to be a -6. So I'll do 3 times row 1 plus, a -2 times row 2. Okay, so if I do that, that's going to eliminate the 3 here. And I want to replace this guy with the result. So this is going to give me a new row 2. This is what we call a row operation. You can multiply rows by a number, you can add the rows together, and we're doing both multiplication and addition of rows. And so let's look at what that appears to be. So 3 times row 1. So I'm going to go to row 1 and multiply all 4 entries by 3. So I'll have 6, -3, 3, and 33. And then I'm going to go to row 2 and multiply every entry by -2, giving me -6, -4, +2, +10. And then I'm going to add those together. 6 plus -6 is 0, which is what we wanted here. -3 plus -4 is -7. 3 plus 2 is 5. And 33 plus 10 is 43. That's going to be my new row 2. Okay. But I also need to eliminate my 4 down here using the 2 again. The 2 is the assassin. The 2 is going to kill off the 3, and the 2 is going to kill off the 4. Whatever entry is up here is going to kill the entries below it to give us our zeros. So this time I want to turn my +2 into a -4, because the -4 will add together with my +4 to be 0. So I'll take -2 times row 1, and I'll add it to my row 3 to give me a new row 3. So -2 times my row 1 entries is -4, +2, -2, -22, and row 3 is 4, -2, -5, 1. And then I just add those together, and I get 0. I also get another 0, -7, and -21. And this is my new row 3. Now, one thing I want to point out is when you add your rows together, what you're doing is getting a new equation. This new row 3 is a new equation. Okay, 0x plus 0y minus 7z equals -21. And so since this is an equation, I can divide both sides by -7, which is handy here because, so I'll just kind of draw a light line through that. This is actually going to be my new row 3, 0, 0, 1, 3, if I divide everything by -7. All right, let's see where we're at. I have a new system now where my first row did not change. I didn't get a new row 1. So row 1 is still 2, -1, 1, 11. But my new row 2 is this guy right here, 0, -7, 5, 43. And my new row 3 is right here, 0, 0, 1, 3. And so I get a new augmented matrix, and we can see that column 1 is set up the way we want here. An entry with 2 zeros below it. So now typically what we do is we would turn our attention now to column 2. And our goal in column 2, remember, is to get a 0 in the third row. And we already have it. So we don't have to do any more work. This system is in row echelon form because we have our triangle of zeros in the bottom left corner. So that's great. We're to a point where we can finish solving the system. Okay, so here's our new augmented matrix. Now, what do we do with this? Well, the reason we like this row echelon form so much is because now each of these rows represents an equation. So for example, row 3 here, row 3 represents 0x plus 0y plus 1z equals 3. In other words, row 3 0x plus 0y plus 0z, or sorry, plus 1z equals 3, well, that's a silly way to write that. Why don't we just write z equals 3? And now we know our z value. So you start from the bottom and you can figure out z. Once you know z, we're going to back substitute. Let me write that term down. We're going to back substitute back up here to row 2. So in row 2, we have 0x, so I'm not going to write that, minus 7y, we don't know what y is, plus 5z, well, z is 3, so 5 times 3 equals 43. And now we can solve this for y. So we get negative 7y, 5 times 3 is 15, and if I subtract that from 43, I get 28. So we can see that y is negative 4. And then we back substitute, so we start at row 3, we back substitute to row 2, then we back substitute again to row 1. So in row 1, we can see we have 2x, we don't know x, minus 1y, so minus 1 times y, which is negative 4, plus 1 times z, so 1 times 3 equals 11. So we have 2x plus 4 plus 3, so 2x plus 7 equals 11, which means that 2x is 4, which means that x is 2. And so the solution here is the ordered triple, where x is 2, y is negative 4, z is 3. This is the x, y, z triple that makes all of our original equations to our system true. Geometrically, each of these equations represents a plane in 3 dimensions, and this order triple is the point where those 3 planes intersect. Okay, let's do one more. I know these take a while, so I'm trying not to make this video too long, but I want to be thorough. Okay, so here I changed the instructions a little bit and just said solve using the augmented matrix. It could say solve using Gaussian elimination. It could say something like put the system into row echelon form to solve. Lots of different things. It might even mention back substitution. But okay, so to get started, we need to create the augmented matrix. Now, the augmented matrix as it sits would be fine. I know in my top left corner of my matrix, I want to use my entry that's here to get zeros below it. And right now, that would mean using a 3 to eliminate the x and the negative 4, which would be fine. However, I know it might be a little bit easier if I used a 1x to eliminate my 3 and my negative 4. So my preference here is going to be I want my x here to be in the top left. So before I even make my augmented matrix, I'm going to interchange row 1 with row 2, and then I'll create my augmented matrix. So row 1 is now going to be x plus 2y minus 4z equals negative 3. So 1, 2, negative 4, negative 3. And row 2 is now going to be 3, 7, negative 15, negative 12. And row 3 doesn't change, negative 4, negative 6, 15, 16. Now we're going to do our column by column assassination of the terms we don't want. So in this case, we want to keep our 1 and use him to eliminate the 3 and the negative 4 through 2 different row operations. So if I turn my 1 into a negative 3, that will eliminate the 3 in row 2. So I'll take negative 3 times row 1 and add it to row 2 to give me a new row 2. We'll write that out momentarily. And then to eliminate my negative 4, I want to turn my positive 1 into a positive 4. So I'll do 4 times row 1 and add that to row 3 to give me my new row 3. All right, let's do both row operations. I went ahead and multiplied row 1 by -3, copied row 2. Now we're going to add these together to get 0, 1, -3, -3. That's going to be our new row 2. Now I multiplied row 1 by 4, and I've copied row 3. And when we add those together, we get 0, 2, -1, 4. That's going to be my new row 3. So I'm going to write my new augmented matrix, keeping my row 1 the way it was, and copying my row 2 and row 3. And we can see our first column is set up the way we want, an entry followed by 2 zeros. Now we move to column 2 and get it the way we want it. And the way we do that now, this is the first one we've had to do that, we want to eliminate this 2. We want that to be a 0. And the way we do that is we use the entry above it. So this guy, my 1, is what I'm going to use to eliminate my 2. It's kind of like the terms that live on the diagonals here. Those are the ones that you use to eliminate the terms beneath it. Okay, so if you went to 4 equations, you would go along the diagonal and use them to knock out all the terms below them. So I need to turn this 1 into a -2 to eliminate this +2. So I'll do -2 times row 2 and add that to row 3 to give me a new row 3. I don't want to change row 2, I want to change row 3. So I've done the -2 times row 2. I've copied row 3. Now we'll add those together to get our new row 3. We get 0, 0, 5, 10. And again, like the previous example, we can see that 5 and 10 have a common factor of 5. So I'll go ahead and divide those by 5 to give me 0, 0, 1, 2 as my new row 3. So now let's copy our final system, keeping rows 1 and 2 the same, but getting a new row 3. When we do this, we can see our lower triangle of zeros here. And once we've got this in row echelon form, we can go ahead and proceed with back substitution, working from row 3 up to row 2, and then from row 2 up to row 1. Okay, so in row 3, we can see that 1z equals 2. Then we back up to row 2, which says that 0x plus 1y, so y, minus 3z, so minus 3 times 2, equals -3. So y minus 6 equals -3. And then add the 6 over to see that y equals 3. So now we know z and y. Let's back up to row 1, which says 1x plus 2y minus 4z equals -3. We can solve this for x. We've got x plus 6 minus 8. So x minus 2 equals -3. And then adding the 2 over, x equals -1. So our solution is the order triple, where x is -1, y is 3, and z is 2. And that is how you do Gaussian elimination with a system of 3 equations and its augmented matrix. Take your time when you do this. Lots of places for errors, lots of arithmetic. So just make sure you're labeling your row operations, multiplying very carefully, adding very carefully. It's faster to go slower on these. Good luck.